Hey guys, it's Eric here. This is our first lesson that's going to be online, and I have no idea what I'm doing, and this doesn't feel very natural to me, but we're going to do the best we can. Hopefully, once I get used to this, it'll start to become more, I guess, natural for me to do, and I won't feel so weird talking to the camera. Anyway, this is going to be the format of our lessons for the next 6 weeks or so, and it's always going to look the same. You're going to see my hands. You're going to see hear my voice. I'm going to be writing notes on this piece of paper here, and you can follow along, take notes if you like, or you can just listen. Obviously, you can watch these videos multiple times. So we'll just see how it goes, and send me any feedback that you have also as to how it's going, whether you can hear me, if I'm being clear, and if there's anything I can do to improve. So today is our first lesson, and it's going to be on RL series circuits. The last lesson we had when we were together was on inductive reactance, and if you recall, inductive reactance the symbol is XL, and it represents the ability of a coil to limit current in a circuit, not because it has resistance, but because it has inductive reactance. And we learned that formula XL is equal to 2 pi FL. I hope I assigned you that homework assignment, and I hope that went well for you. And if you have any questions about it, you can just let me know. But this is going to be RL series. So RL series. I might have to get some, I don't know, better markers. Now, the reason we're doing RL series circuits is because if you have a coil, we know it has inductive reactance, but it's also made out of copper, and so it has resistance as well. And actually, both a coil's inductive reactance and its resistance work together to limit current in the circuit. And because a coil has both inductive reactance and resistance, the circuit behaves a lot like a series circuit, even though it's one component. So anytime you have a coil, it'll be one component. It has inductive reactance and resistance, but because they work together and the same current flows through both, it behaves exactly like a series circuit, and so you can draw it as two separate components, a inductor and a resistor. Now this would be XL here. This would be the coil's inductive reactance, and this component here would be its resistance. And like I said, even though it's one coil, we can draw them as two separate components and put them in series and see what's going on with that. Now, before we even bother looking at RL series circuits, let's just do a quick review of level 1, really basic review on series circuits. And so let's say I had just 2 resistors in series. Let's go over the rules for series circuits. So if I had 2 resistors like this, and one was 10 ohms, and the other one was 15 ohms, then the first rule for all series circuits is that there is one current, right? Second rule for series circuits, and that was this one. If I want to figure out the total resistance of the circuit, well, RT would be the sum of all the resistors in the circuit, so it would be R1 plus R2 plus R3, dot, 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 if there was more than 2. The third rule for series circuits is, well, let's say I had, a voltage up here, and I don't know, just for fun, it's going to be 50 volts. I can apply Ohm's law to the individual components in the circuit, and I'm also able to apply Ohm's law to the entire circuit. So an example of applying Ohm's law to the entire circuit is, let's calculate the total resistance first of all. RT for this circuit is going to be 25 ohms. It's going to be 15 plus 10. Since I know E total, it is 50 volts. Then I can apply Ohm's law to this entire circuit. I would be E over R, 50 over 25. And so current would be 2 amps. Okay, so that's always going to work. You're always able to apply Ohm's law to the entire circuit. But I can also apply Ohm's law to the individual components in the circuit. And now that I know that the current is 2 amps, I could actually calculate the voltage here and the voltage here. ER1, it will be IR1 times R1. And so in this case, it would be 2 times 10, 20 volts, right? And I could calculate ER2. It's going to be IR2, which is 2 amps. I mean, it's the same current in the whole circuit. So it's going to be I times R2. And in this case, 2 times 15 is 30 volts. So, yeah, Ohm's law to the whole circuit or Ohm's law to the individual components of the circuit. That's no problem at all. And then the last rule that I want to talk about for series circuits is that the sum of the voltage drops in the circuit should add up to the voltage rise. So the formula, as we learned it in level 1, was E total. Well, it's equal to ER1, plus ER2, plus, dot, dot, dot. And so in this case, I could check that E total should be the sum of the 2 voltage drops in the circuit. And so 20 plus 30 equals 50 volts. And that is indeed our voltage rise in the circuit. So everything is working out for this circuit right here. Now, all the rules that we learned in level 1 about series circuits will apply to our RL series circuit in level 2. So let's actually figure out what's going on here. This is going to be an AC circuit of some sort. And let's put some numbers to this. Let's say XL for this circuit is, 45 ohms. And the resistive part of this coil, let's say it is 35 ohms. And just for fun, let's say this is 100 volts AC over here. Now, if I want to figure out what's going on with this circuit, the first thing I need to know is the total resistance of this circuit will be the sum of all the gadgets that limit current in the circuit. And right now we have 2 gadgets limiting current in the circuit. One is the resistance of the coil, and one is the inductive reactance of the coil. Now, the first thing we need to say is the sum of all the gadgets in the circuit that are limiting current is no longer going to be called RT like it was in level 1. Okay? RT is R1 plus R2 plus R3, and that works in level 1, and it works for DC circuits, and it works for circuits that only have resistors in it. In an AC circuit where you have more than one type of component that limits current, the new, RT that we use is called Z. It's the impedance of the circuit. So the impedance of the circuit is always the sum of all the gadgets in the circuit that are limiting current. And impedance, well, its symbol is Z, okay? So this symbol here, Z, is always going to represent the impedance of the circuit, and the impedance of the circuit will always be the sum of all the gadgets in the circuit that limit current, and it is measured in ohms. Okay, same symbol, and I think I said to you last week that anything that represents something that limits current in the circuit is going to be measured in ohms. So now we have the resistance of the circuit measured in ohms, inductive reactance of the circuit measured in ohms, and then the impedance of the circuit, which is the sum of the two, it is also measured in ohms, and its symbol is Z. Now, if I want to figure out what the impedance of this circuit is, I have to add these two up. But I can't just add them up like 35 plus 45 because these two things have different phase angles. And if you recall from last week, if I have a resistor in the circuit, it causes the current to be in phase with the voltage, but an inductor in the circuit causes the current to lag by 90 degrees. And so if I'm going to add these two up to figure out the impedance of the circuit, I've got to add them up as phasors. And so we're going to draw our little phasor world here and see if we can figure out how these are going to look. Now, this is a series circuit, and since there's only one current in the circuit, we're going to compare all our phasors to the current in the circuit, and so we'll just represent this horizontal line as the current, and we'll draw these two phasors as phasors with respect to the current. And since the resistor is 35 ohms and a resistor causes the current to be in phase, we're going to draw that resistor right here in phase with the current. We'll call it R, and it is 35 ohms. Now, the inductor reactance of the circuit, inductors cause the current to lag by 90, which means I have to draw this 45 ohms out of phase from the current by 90 degrees. And so then the only question is, do I draw it straight up or do I draw it straight down? And the answer to that is we're going to draw it straight up. And the reason for that is it needs to be drawn in such a way that the current is clockwise by 90 degrees. So it sits right here leading the current since the current is lagging. And if you remember from last week, lagging phasors are always drawn clockwise and leading phasors are always drawn counterclockwise. So if I draw that 45 ohms leading the current or with the current lagging, I must draw it clockwise or counterclockwise by 90 degrees straight up here, but I have to move it tip to tail. So that's what I'm going to do. It's going to sit right here. This is going to be XL. It'll be 45 ohms, right like that. And the sum of the two, well, it's going to be a line that starts at the beginning of the first one and ends at the end of the last one. And so that'll be a line that sits right there. We're going to call it Z, and you can probably already figure out that I can calculate Z. It's going to be 35 squared plus 45 squared square root. And so I got my handy calculator here. We're going to calculate that right now. I don't know if you can see that or not. Doesn't matter. I'm going to go 35 squared plus 45 squared equals square root equals, looks like it's 57 ohms. Stay tuned for part 2.